Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at ChemAdvantage.
Mass spectrum charts are an important part of AP Chemistry, and that's what this question is about. So let me explain what mass spectrum charts are and how to interpret them. We'll start off with a periodic table because that's what we're dealing with. We're dealing with elements. Here we've got a table, and we're going to start off with fluorine. And as you can see, we've got two numbers here, fluorine with a 9 and a 19. Now, this 9 indicates how many protons an average fluorine atom has. Now, I'm going to go to a mass spectra of fluorine. It's one of 18 elements that consist of just one type of atom. Originally, Dalton thought that all the atoms of an element were the same, but we found out that that's not always true, that there are some slight differences. But fluorine is one element whose atoms are all identical. Every fluorine atom has 9 protons and 10 neutrons. Now, protons and neutrons weigh about 1 atomic mass unit. Atomic mass units used to determine the weight of atoms. An AMU weighs about 1.7 times 10 to the negative 27 grams. AMU is a thousandth of a trillionth of a gram. But it's great for measuring atomic mass because you can use nice numbers like 19, which is much easier to say than 3 times 10 to the negative 26 grams. Now, this is a measured value. It's a weight. And here we've got just whole numbers here, but realize that there's going to be a decimal point here. Now, as I said, fluorine atoms consist of only of one type of atom with 9 protons and 10 neutrons, each weighing 1 AMU, so the total weight is about 19. So here we've got the weight of the atoms. That's part of a mass spectrum graph. And here we've got on the y-axis percent abundance, which says how many atoms are like this. So here we've got 100%. 100% of fluorine is exactly like this. A nice simple graph. But when you get to copper, even though every copper atom has 29 protons, some copper atoms only have 24 neutrons. Now, 29 and 24 add up to 63. This is the weight because protons and neutrons weigh about 1 AMU each. And here we've got a graph of it saying, oh, there's a whole bunch of copper 63, total weight of 63 AMUs roughly, the version that has 24 neutrons. But it's only about 70% of our sample of copper. If you look at a copper wire, every single atom has a total of 29 protons because look here at our periodic table, copper, 29, exactly the number of protons. That identifies copper. But only about 70% of the atoms of a sample of copper from anywhere is this type of atom. Here is our detail, 69.09% of copper, and this is the copper 63 with the 24 neutrons, and each one of those weighs 62.93. Notice that it's not exactly 63. It'll round off to it. There's some extra factors in the weight of a nucleus that make this number not exactly what you'd expect. But these 70% are this type of copper. Well, what about the rest of the copper? Well, there's another type of copper. It's orange, it's shiny when you have a lot of it, conducts electricity, does everything chemically like copper would do, but this copper has an extra couple of neutrons in its nucleus. And because of that, it weighs about 2 MUs more. Notice here we've got 63 AMUs for the guys missing the 2 neutrons, if you consider that neutron. And here, 2 more AMUs, extra weight of 65. Now, there's not as many of them. As you can see, is about 30% of the atoms. So here it says 30.91% of copper atoms have a total of 26 neutrons, making them a little bit heavier. But that's all it does. It just makes them a little bit heavier. So while Dalton said all atoms of an element are the same, that's not really true for many elements. There are some elements that end up having a mixture where some of the atoms are a little bit heavier because they've got a couple of extra neutrons, or lighter because they're missing a few neutrons. And this can be determined by a mass spectrum, where you separate the atoms by their weight. It's a very sophisticated machine, but you're seeing a lot of use of it, especially in forensic science. And we'll have a little section on how these things work. But you can sort atoms out using a mass spectrum, and this is a graph of it. Now, of course, this can lead to some really interesting questions that you're going to find on an AP exam in all sorts of ways. And we're going to go over one of the types of question, and that's what this says. The atomic mass of copper as a naturally occurring element to 4 significant digits. Well, atomic mass of copper, well, isn't it? Well, which one is it? Well, it's a blend of these. The atomic mass of copper is a blend of these 2 types of atoms. We're going to have to calculate that blend. Now, you can look at the graph and say, okay, we got a lot of 63 weight. We've got less 65. So the average, which is what we're looking for, is going to be somewhere in between 63 and 64. If they're both 50%, then we know it's 64, but it's not. So how do you do a calculation like that? Well, it's a percentage and a weight. So we have a percentage, decimal equivalent, times what it weighs. So this is the weight contribution of 100%. Now I'll pull out my calculator. Calculator time. Bingo, here it is. Oh, those are the answers. Here it is. So let's do that calculation. Decimal equivalent of the percentage. 69.09 times its weight. Again, you could round off to 63, but we want an accurate answer. So I'm going to put this down, 62.93. Like I say, you could have just used 63, but we got the calculator. So let's get the exact answer. So the weight of this portion is going to be, because we're going to add it up to 100, is 43.4. Okay, 4 significant digits. We'd make that 43.48 AMUs. If this was an FRQ and you were asked to do this, and you had to show your work, I mean, you did that calculation, you have to show your work. If you don't show your work, you get no points, even if you get the right answers. They presume you cheated, but so that's it. You got to show your work. Anything you want to do on the calculator, you've got to do on your paper when you answer a free response question. Well, okay, that's this component. This one only has 2. Some elements have like 5, 6, 7 components, so this is going to be an easier one. So, same calculation. We're going to end up taking the decimal equivalent and figure out that weight and then add the 2 together. So let's go back to our calculator to use it efficiently. We just did this first answer. We're going to need it. So store it. Store it as X. You wrote it down on your FRQ, but this is efficient. See that little store button? And this X is like a default. You're going to use that a lot. So I'm going to enter. And now I know whenever I type in X, I'm going to get 43.48. In fact, if you turn the calculator off and on again, it's still going to be there. X will be this value till you change it. But let's get this. Here we go. Calculate. 0.3091. Don't use the 30. That's a common mistake. Times its weight. This is the heavy stuff. Times, they got 2 extra neutrons in there in its nucleus, 64.93. Still the same number of protons, 29, but it's got those 26 neutrons in there. And let me get that 93 in. AMUs, enter. Now, this is the weight that this extra isotope has. And of course, if we put them both together, and this is where it's nice with these calculators, I'm just going to say take this last answer and add to it. And add to it, I'm not going to type in 43.48. I might get that wrong. X. Enter. 63.55. So I would write all that down on an FRQ. I'd have my answer, the 20.07 contribution of the weight. This is this weight, and the 43.48 is this weight in any mixture. We add them together, and again, write this out. This is the average. When you look at some copper and you take a bunch of its atoms and average them together, their weight won't be 63. Their weight won't be 65. They're all mixed in together. It's going to be 63.55 AMUs. So this is how you calculate it. But if this had been a question that had given you this graph, and asked what the average atomic mass was for copper, don't do the calculation because, ta-da, periodic table of elements has done that for you. 63.55, that's the average weight. What you see here are the average weight of the mixtures of isotopes of each one of these elements. Now, like I say, some of these elements have only one isotope, like fluorine only has fluorine, period. One type of atom that has the 9 protons and 10 neutrons. But most of the elements are mixtures of various isotopes. So let's go back to our problem. Now, again, you could have answered this instantly using the periodic table. But of course, think as somebody who's writing up AP exams. You can do all sorts of neat things. You could say, okay, I know the average, and I know one of the isotopes percentages, contribution. What's the other isotopes? And we'll get into those problems later. But understand what a mass spectrum chart is about. It's about an element and the different portions of isotopes, where some of the elements are heavier or lighter than others. And we've got our percentages, we've got our rounded off weights here, you understand AMUs, and you understand the average, and you know that the periodic table is going to be your friend. Whenever you do a mass spectrum problem, look up that element on the periodic table. You will have to. Okay, that's it. An explanation of mass spectra and isotopes, and we'll be seeing more of these on other problems and also on the AP exam.